you haven't done so yet, please pause the video and try to solve the question before listening on. Our first step is actually to convert the frequency from beats per minute into hertz. And to do that, we can write the frequency as 115 beats over 1 minute. Now, to get into frequency, we need the unit of cycles per second. We can assume that 1 beat is equivalent to 1 cycle. And when we arrange the conversion this way, the beats will cancel out. And then, of course, we know that 1 minute is equivalent to 60 seconds. And then we can eliminate the minutes. So we'll go ahead and calculate this frequency. And we get roughly 1.917 cycles per second. We can write cycles per second as hertz. So this is the standard unit for frequency. Now with this value, we can go on to calculate the maximum linear speed of the heart. Since we know that that maximum speed for harmonic motion is equivalent to the angular speed multiplied by the amplitude of the wave. Now angular speed is equivalent to 2 pi times the frequency, so we're going to have to make a substitution for the angular speed. And then once we do that, we can substitute in the value for the frequency that we just determined, as well as the amplitude. Note that the amplitude was given in millimeters, so we're going to have to multiply that value by 10 to the minus 3 so that we convert it into the standard unit of meters. And this turns out to be roughly 2.16 times 10 to the minus 2, and then the standard unit of speed is meters per second. So there we have the correct answer to part A. Now to part B, we're going to see that it's an application of the Doppler effect. So let's go ahead and write out the formula for the Doppler effect. So here we have the Doppler effect equation. Why don't we go ahead and also write down what each of these variables represents. So here are all the variables defined. You probably want to pause the video and read through this just to make sure that they all make sense. In this question, we're going to assume that the observer is the heart wall, and that the source is the detector mentioned in the question. Now, to fully understand why we're making those designations, here's a relatively crude drawing showing the scenario described in the question. So the mother's abdomen has this motion detector pressed up against it, and we can assume that that detector is stationary. It is the fetus's heart that we're trying to detect with this equipment, and as the question notes, that fetus's ventricular wall is moving in simple harmonic motion. So we can assume that that heart is actually the moving object. And that's why we're calling the observer the heart wall, and then the actual source is going to be this detector, which is sort of emitting a sound source towards the fetus's heart. Now, the detector itself is stationary, so we know that the speed of that source is going to equal 0. And so in the equation, we're going to end up eliminating this term. And then as we figured out in part A, the speed of the observer, or the heart wall, is that value that we determined, that 2.17 times 10 to the negative 2 meters per second. The speed of sound v is given to us in the question. We just have to multiply that by 10 to the third to get it into a standard unit. And then finally, f sub s is stated as 2 megahertz, but that needs to be converted into hertz by multiplying by 10 to the sixth. So with all that in mind, we'll go ahead and plug into the Doppler effect equation. So here are all the values plugged in. When we simplify this, we get approximately 2,029 hertz. Not much different than the frequency emitted by the source, and that's because the heart is not moving that rapidly relative to the speed of sound. But nevertheless, the frequency is a little bit bigger. So this is the correct answer to part B. Now in part C, they're mentioning that the sound is reflected and then received by the motion detector. So in this case, because of the echo, the heart is now going to be considered a moving source, and the detector a stationary observer. And so since the observer in this scenario is stationary, we can say that v sub o is equal to 0 meters per second. That's going to eliminate this term right here. The frequency of the source would be the frequency that we determined in part B. That is the frequency that the sound had arrived at the wall of the baby's heart with. So when we plug in for f sub s, we're going to be using the value from part B of the question. remembering that the speed of sound was stated in the question as 1500 meters per second, and that the speed of the source in this case would be the speed of the moving heart, which again was figured out in part A, we can plug in those known values and calculate the frequency of the stationary observer. And when we simplify that, we get approximately 2,058 Hertz. And so that would be the correct answer to part C. Thanks for taking the time to watch the video. If you liked it, please click the thumbs up icon. Also subscribe to the channel so you can stay tuned for additional videos. If you send in your own question to this email address, I'll do my best to answer it on YouTube.